Okay, welcome back everybody. Let's go ahead and talk about balancing redox equations. All right, so this is it's simple and it's complicated. We're really just going to talk about one thing, how to balance redox equations. So in that sense, it's fairly simple, but balancing them is a multi-step process. So we're going to have to go through several steps, and that can be seem a little bit complicated. So there is a specific strategy for doing this. That strategy is, I'm sure it's in all of the textbooks. I've also put the strategy down in a list of steps in the study guide. You can find it there, and I'll go through the steps here with you fairly quickly. And then after we do that, we're going to do one example. As I said, there are a lot of steps in these, so balancing one redox equation can take sometimes 10 or 15 minutes, believe it or not. So we're going to go through one of those, and I think just one of them is plenty to show you how this works. And then, of course, obviously there are more examples that you can look at in any of the textbooks, and there are a couple of completed examples in the study guide as well. All right. So the strategy, I think there are about 6 or 7 steps. First step, assign oxidation numbers to all of the species to determine what's being oxidized and what's being reduced. Uh, did a whole video on determining oxidation numbers. So if you need to refresh that, you can go back and look at that one. We'll assume we've got that down. Next, once you have figured out what's being oxidized and what's being reduced, break those two different parts of the equation up into two separate reactions called half reactions. We'll have an oxidation half reaction for the oxidation step, a reduction half reaction for the reduction step. All right. Then for both of the half reactions, predict the number of electrons that are being lost or gained. Okay, that's not actually 100% essential, but it's often helpful because at the end we're going to balance the charge by adding electrons, and it's nice when we see that the number of electrons that we predicted at the beginning matches the number of electrons that we end up adding at the end. That always makes us happy and gives us an idea that we are on the right track. All right. Next thing is to balance all of the exotic elements. That means, metals and metals, non-metals, anything that's not hydrogen and oxygen. We've got a special technique for balancing hydrogen and oxygen. So everything else are the exotic elements. Where you might see this, usually you'll have things like, well, in this example that we're going to have in a minute, we'll have permanganate going to manganese. So the exotic elements would be the manganese, okay? And there's one on each side, so they're already balanced. 9 times out of 10, at least 9 times out of 10, the exotic elements are already balanced, okay? But occasionally, like if you have dichromate, for example, that's a minus. So if you've got the dichromate ion going to chromium 3, the first thing you need to do is balance the chromiums. And because there are 2 chromiums on the left and only 1 chromium on the right, you need to balance them by putting a 2 there. Okay, like I said, 9 times out of 10, the only thing you have to balance are the hydrogens and the oxygens, but do be careful to make sure that everything else is balanced as well. That's the first step that you want to do. Balance your exotic elements. Also, I'll make another note on this. If you're balancing this, right, and you say that chromium, if you do all of your oxidation numbers, you'll see that chromium in this case is going from +6 to +3. you would predict, I hope, that that is a 3-electron process and that the reaction ought to have um, 3 electrons in the balanced equation. When you get to the end, you're going to find in this case you've actually got 6 electrons in the balanced process. And the reason you have 6 is because you've got 2 chromiums. So if you have to multiply that exotic element um, by some number, then you're also going to be transferring twice that many of electrons, right? All right, I just wanted to point that out. Again, like I said, not an issue 9 times out of 10, but it does come up occasionally. I'm sure there's some, at least 1 or 2 in the book and in the study guide that will do that. All right. Once you've got the exotic elements balanced, balance the oxygen by adding waters. If the reaction is taking place in solution, as most of them are, there's plenty of water around, so you can assume that the water is taking part in the reaction. You can add that in as either a reactant or a product, either one as you need. Okay. Then once you've balanced the oxygens, then balance the hydrogens by adding H plus. Reactions, redox reactions, when you have a problem, it'll usually tell you that you need to balance it either under acidic conditions or basic conditions. What the trick that we're going to do to make this a little bit simpler, most of the textbooks do it this way. I'm not sure if they all do, but it's much simpler to balance under acidic conditions than basic conditions. So what we're going to do is we're going to assume in all cases that we're balancing it under acidic conditions. And if it's acidic, there's a lot of H plus available. So we'll just add H plus as a reactant or a product as needed to balance it. And if it's basic, we'll correct it at the end to change it from acidic conditions to basic conditions. All right, and then the last step for this is just for balancing the half reactions. The last step for balancing the half reactions is to check the number, is to add in electrons to balance the charge. Okay. All right, once we've balanced the half reactions, we're going to multiply each one so the number of electrons in the reduction reaction is the same as the number of electrons in the oxidation reaction. Okay. Remember, I'm curious if my audio quality just got better because there was something wrong with my mic that I just fixed. Remember that all the electrons released from the oxidation process have to be consumed by the reduction process. So we need the number of electrons to be the same in both reactions. All right. Then we're going to add the reactions together. Often when you do that, you end up with water on both sides or hydrogen ions on both sides. You can do a little bit of canceling and simplification. All right. Then, if we have to balance under basic conditions, we're going to fix that by neutralizing all of the H plus by adding hydroxide ions. That way, our reactions are going to contain hydroxides instead of hydrogens, and it will be suitable for basic conditions. The thing you have to remember with that is chemical equation is a lot like an algebraic equation. Anything you add to one side, you have to add to the other side. So if we add 6 hydroxides to the reagent side, we also have to add 6 to the product side. All right. Then when we're done, the final step is to check the balance. And in this case, we're going to check the balance not just of all of the atoms, but also the total charge. Okay. It's important to note when you're balancing the charge doesn't have to be 0 on both sides. It doesn't have to be neutral. The only thing that has to be true is that it has to be the same on both sides. If it's +6 on the left and +6 on the right, that's fine. Okay. All right. Now let's look at an example. All right. So we've got permanganate reacting with iron 3 to make manganese 2 plus and the ferrate ion. Ferrate ion is fairly unusual. You may not have seen that one before. But this is our reaction. And as I said before, normally it would say balance this reaction under acidic conditions or balance it under basic conditions. Since we're just going to do this one example, we're going to balance it first under acidic and then under basic. So we'll do both with this particular one. All right. The first step, of course, is to assign oxidation numbers to everything, just as we did before. So let's take our permanganate ion to begin with. We'll write our algebraic equation. Okay. The oxidation number of manganese plus 4 times the oxidation number of oxygen is equal to -1. Of these, oxygen is obviously the most electronegative, so it gets its preferred negative charge, which is -2. So manganese is +7. Okay. And oxygens, sometimes, particularly if you have a peroxide or sometimes oxygen gas, if you've got, yeah, those are the most common, oxygen gas and peroxides. But the oxygens actually can be participating in redox equations, so we want to make sure we note their oxidation states as well. So manganese is +7, oxygen is -2. All right, and the iron, of course, is +3. Manganese here, this is easy, is +2. And then we've got this ferrate ion here. So I'll just whip through this one. You guys might have already beaten me to the end on this one. All right, so iron is +6. And the oxygen here, of course, is -2. All right, so now that we've got our oxidation numbers, we want to check and see what's being oxidized and what's being reduced. And this actually is a good early point to do a check and make sure that you haven't made a mistake. You've got to make sure, of course, that you've got one thing being oxidized and one thing being reduced. If both things are being reduced or both things are being oxidized, guarantee you've made a mistake. You need to go back and redo your oxidation numbers. All right, so manganese is going from +7 to +2. That's a reduction. And iron is going from +3 to +6. That's an oxidation. Okay, great. So we've got our reduction half reaction with manganese, our oxidation half reaction with iron. We're just going to balance each of those two half reactions separately. Okay? And that'll simplify things a little bit. All right, so here is our oxidation half reaction. Fe3 plus going to Fe4O2. All right, remember our steps. The first step is to balance the exotic elements. The exotic element here would be iron. There's 1 on each side, so it's already balanced. The next step is to balance oxygens by adding water. And we've got 4 oxygens over here, so I'm going to add 4 waters to the left-hand side. We want to make sure we have states in our final balanced reaction, but you can leave them out in the intermediate steps if you would like. All right, So we balanced our oxygens. We've got 4 on both sides. Now we have to balance the hydrogens. Oh, let me back up a minute. Um, we said one of the things that's helpful is to predict the number of electrons. And if iron is going from +3 to +6, that means it must be losing 3 electrons to go from +3 to +6. So we should end up with 3 electrons as a product in this reaction. Let's just keep that in mind and see what happens when we get to the end. All right, we've balanced oxygen. Now we have to balance the hydrogens. We've got 8 hydrogens over here. So we balance by adding 8 hydrogens over here. All right. And now we want to balance the charge. Okay. And again, it's not necessary that the charge is equal to 0. It's just necessary that it's the same on both sides. All right. On the left-hand side, we have, we've only got one thing on the left-hand side with the charge. We've got an iron 3+ ion. So that's a charge of +3. And on this side, we've got this ferrate, which is -2. We've got 3 hydrogens, which is +8. And so that means our total on this side is +6. Okay. All right. So we want to balance this charge by adding electrons. Remember that electrons have a charge of -1. So if we want to get the same charge on both sides, we're going to have to add 3 electrons to the right-hand side. If we do that, now the total on the right-hand side, -3 there, total on the right-hand side is +3, and the total on the left-hand side is +3. Okay. All right, let's do the same with our reduction reaction. All right, our reduction reaction is MnO4 going to Mn2+. First, we want to balance the exotic element, and that is manganese in this case. There's 1 on each side, so that's already balanced. Next, we need to balance the oxygens by adding water. We have, again, 4 oxygens on this side. So we'll put 4 waters over here. Oh, I forgot the electrons again. Manganese in this case is going from +7. The oxidation number is +7 to +2, which means it's gaining 5 electrons. So when we get to the end of this, we expect that we're going to need to have 5 electrons in our balanced equation. We'll see if that happens. All right. We've balanced our manganese, we've balanced our oxygen. Now we have to balance our hydrogens. We've got, again, 8 hydrogens over here. So we'll add 8 hydrogens over here as H+ ions. Okay. All right. And now let's look at our charge, right? Not the oxidation numbers, not these guys, but the total charge. We've got +8 and -1 is +7. And over here, we've got +2. All right. So we want to make these the same by adding electrons. And since electrons have negative charges, if we add 5 electrons over here, that'll decrease our charge by 5, 2+, so those will be equal. So I'll put 5 electrons in there. All right. And that is our balanced reduction half reaction. All right. Let's look at the next step. All right. Our next step is to multiply each reaction so that the number of electrons produced in one reaction is equal to the number of reactions consumed in the other reaction. And when you do this, sometimes the numbers can get pretty big, and that's why you need to be really, really careful with these. You've got to go slow and methodically, because sometimes you get some pretty big numbers. All right, we've got 3 electrons over here, 5 electrons over here. What we're really doing is trying to find the least common multiple. Back something you did probably in 2nd or 3rd grade. The least common multiple of 3 and 5 is 15. So we'll take this reaction, multiply it by 5. We'll take this reaction and multiply it by 3. And that's going to give us, very carefully, this reaction. We get 5 irons plus 20 waters goes to 5 ferrate ions plus, good gravy, it looks like 40 hydrogen ions plus 15 electrons. Okay. And in our reduction reaction, we get 15 electrons plus 3 permanganates plus 24 hydrogen ions goes to 3 manganese plus 12 waters. Okay. All right, and then on the then once we've got these two, all we need to do is add this reaction and this reaction. When we add them together, there's going to be a little bit of canceling to do. All right, and because this is getting a little bit jumbly, I'm going to do that on the next page. All right, so here is our oxidation reduction half reactions after we've multiplied them by an integer. The first thing you want to check is to make sure that you have the same number of electrons on both sides, because that was the whole point of the last step. We've got 15 electrons over here, and we've got 15 electrons over here, so we can cancel those out. Okay. Then you very often end up with hydrogen ions and or water molecules on both sides, so we want to look at those and see if we can do some canceling. So for waters, we've got 20 waters over here and 12 waters over here, so we can cancel 12 of those. If we get rid of 12 waters from both sides, that leaves us with no water over here, and it leaves us with 8 waters here. And for hydrogen ions, we've got 24 here and 40 here. So if we cancel 24 of them on both sides, that leaves us with 16 on the right-hand side. And if we add this whole thing up, we're going to end up with 5 iron 3s plus 8 waters plus 3 plus 3 permanganates goes to 5 ferrate ions plus 16 hydrogens plus 3 manganese 2 plus. Okay. All right. That's essentially, if we're balancing it under acidic conditions, we would essentially be done at that point. Although, of course, we want to include states in that. Let's go to the next page so we can have a little bit more space and we'll check that. All right. So this is what we got when we combined everything. 5 iron 3s, 8 waters, 3 permanganate, 16 hydrogens, 5 ferrates, and 3 manganese 2 plus. Okay. Now what we want to do is we want to check each one of these, every species in here, all of the atoms and the charge. So I'm going to make a little table of everything we've got. We've got iron, we've got manganese, we've got hydrogen, we've got oxygen, and we've got charge. Now I'm going to look at the reactant side and the product side. And again, the numbers here are kind of big. So even though we're all grown-ups, the numbers are big enough that it can be easy to make mistakes. So we want to be really careful here. All right. So look at iron first. This is pretty easy. We've got 5 irons here and 5 irons here. 5 and 5. Check. Manganese. Got 3 manganese here, 3 manganese here. That looks good. Now hydrogens. This can be kind of tricky. We've got 8 waters. Each one's got 2 hydrogens, so that's 16 hydrogens. And on the product side, 16 hydrogens. Check, check. Oxygens. All right, we're going to have to do, I have to be really careful with our oxygens because they're spread out over a couple of different species. All right, so we've got 8 oxygens here in this water, and we've got 12 oxygens here, right, in the permanganates. So 8 plus 12 is 20. 20 oxygens on the reactant side. And on the product side, we've got 5 ferrate ions. Each one's got 4. So we've got 20 oxygens on that side as well. Yay. And then we'll check the charge. All right. On the left-hand side, again, it's not important that the charge is equal to 0. Just needs to be the same. So on the reactant side, we've got plus 15, and then we've got this should be up here. That superscript didn't come out. So we've got 3 permanganates, so that's minus 3. We've got a total charge of plus 12 on the reactant side. Now on the product side, we've got 16 here for the hydrogens. This here, each ferrate has a 2 minus. We've got 5 of them, so that's minus 10. And then we've got these 3 manganese 2 pluses, so that's plus 6. And that whole thing comes out to plus 12. Check. All right, so we can check that, and we see that everything is correct. If you can work through that table and everything checks out, then you are essentially done. Like I said, you could be asked to balance these under acidic conditions or basic conditions. If the question asks you to do it under acidic conditions, then you're done, and that's it. Okay. If you need to do it under basic conditions, there's one more step that we need to do. So let's take a look at that. All right. Now, to balance under basic conditions, the easiest thing to do is to just go ahead and balance it under acidic conditions and then do a conversion at the end. And the way we're going to do that conversion is by adding enough hydroxide ions to neutralize all of the hydrogen ions. And you can see here we've got 16 hydrogen ions on the product side. So I'm just going to add 16 hydroxides. And anything you add to the left side, you've also got to add to the right side. So I'll add 16 hydroxides there. Okay. Now, on the right-hand side, the hydroxides are going to react with the hydrogens to make 16 water molecules. And once you do that and combine these to make water molecules, very often there's an opportunity to do more canceling. And you can see that's the case here because now we've got 16 waters on the product side and we've got 8 waters over here on the reactant side. So what we'll do is we'll just subtract 8 waters from both sides. If we subtract 8 waters over here, we get nothing. If we subtract 8 waters over here, our 16 waters become 8 waters. And then now we can just rewrite this. There, our waters are gone. They've canceled out. And then the 16 hydroxides that we had to add, we'll put those in. And then on the product side, all of this business has been converted to 8 water molecules. All right. And 3 manganese ions again. So if you are required to balance this under basic conditions, this would be your final result. And I would encourage you at this point, even if you checked it before, you might want to go ahead and check it again. You could do that check at the acidic stage and then add the hydroxides like this and then check it again, or you could just check it at the very end after you've done the hydroxides. All right, so when you're done with that, you want to check the balance. All right, so here's what we had after we added hydroxides to both sides. You'll want to check the balance with regard to iron, manganese, hydrogen, oxygen, and charge, reactants, products. I tell you what, why don't you go ahead and pause. I'm going to check it here. You check it on your own and then unpause and see if we got the same numbers. Okay. I admit these were actually kind of tricky. Just counting things can be a little bit of can be a brain stretcher. Um, 5 irons on both sides, that was easy. 5 manganese on both sides. Hydrogen 16 on both sides, that's pretty straightforward. For the oxygens, you got 12 oxygens here, right? And 16 here, so that's 28. And for here, we've got 8 oxygens here and another 20 here, that's 28. Okay. The charges on the left hand side, we got 5 of the iron 3 pluses, that's plus 15. We've got 3 of the permanganates, that's minus 3, and 16 hydroxides, that's minus 16. That whole thing comes out to negative 4. And on the product side, we've got 5 ferrates. They have a 2 minus charge, so that's minus 10. And then we've got 3 manganese 2 pluses. It's a total plus 6. So that's minus 4 as well. Yay. All right. So if you had to balance this under basic conditions, this would be your final answer. All right. So summary of this, follow the strategy, practice doing it a couple of times. As you can see from this example, they do take a long time working through them and all of those steps, but that's generally necessary to get them right. They're not too difficult. All of the steps are simple. It's just that there's a lot of steps. There's a lot of opportunities to make mistakes. So go slowly and carefully. And I would say most importantly, particularly, if you've got all the time that you need, definitely do that check at the end. Check to see if it's right. There's really almost no excuse for getting it wrong because you can always check your work at the end. Not all problems are like that, but these are, which is nice. So you can always check to make sure you got it right. Please do that. And if you see a problem, I hate to say it, but go back to the beginning and uh, see if you can find the problem and fix it. All right. Have fun, everyone. This is kind of like the ultimate challenge of general chemistry, balancing redox equations. So have fun with them. And when you get one right, give yourself a pat on the back, maybe a donut or cupcake, something like that. You will have earned it. All right. And I will talk to you again next time.